Hi, I'm Filip Aronshtein.
I'm Peter Weiss.
That's Jeff on the computer.
Oh my god, this is our VCO. So first, I'm going to explain this current source. So the current source uses this potentiometer to create Vin, this PNP BJT, and this op amp here. So the inverting input, the non-inverting input of the BJT is connected to Vin here, which goes through this potentiometer, so we can change Vin. The inverting input is connected to 5 volts through, through this resistor, and because these are two inputs of an op amp, this input to the inverting input is the same as the non-inverting input, which is Vin. Therefore, the current that goes through this resistor here is 5 volts minus Vin over the resistance, so the current varies linearly with Vin with a negative slope. And by the way, this Vin that we use is a voltage source, a voltage supply that's separate from the digilant, so we can use the voltage supply from the digilant for our Vref. So this is 5 volts that I just happen to have as a separate source. But yeah, so this current decreases linearly as we increase Vin, and because this is also connected to the collector of this PNP, the emitter of this PNP transistor, the collector current is about the same as the emitter current, meaning the current through the emitter here varies linearly with Vin, so long with a negative slope, so long as this PNP transistor BJT stays in active mode. And that's our constant current dependent on Vin. And we can see how that current varies with voltage from this graph here. So as the voltage gets close to the power supply voltage of 5 volts, the current's basically 0 because the voltage drop across the resistor is basically 0. And then the current increases as we decrease Vin, meaning we increase the voltage drop across the resistor from 5 volts to Vin. We could go past 3 volts here, but it's just that our VCO doesn't really work when this is less than 3 volts, so we just stopped about at 3 volts. So the current increases linearly as we decrease Vin.
Okay, so now I'm going to tell you about the Schmidt trigger. So as Peter was mentioning earlier, we have a constant current source coming in through this diode. That feeds into an op amp over here. The constant current source feeds into the inverting input of the op amp, and then into the non-inverting input of the op amp, we have Vref coming in through R1. Then we have...
And Vref is from the power supply voltage from the digilant, because we didn't really want to use the voltage divider, so we just decided to use that power supply voltage that we had access to, and it's around 1.7 volts.
Yeah, that's how we solved the problem instead of just, the email that we got from Professor Foster. So anyway, then we have the... Then we have the output of the op amp going in to that point of contact of where R1 goes into the non-inverting input. That goes through RF, and that causes there to be a positive feedback loop, which causes our Schmidt trigger to be unstable. So ordinarily, a Schmidt trigger functions by having 2 thresholds, an upper and a lower one. And when your input reaches an upper threshold, it would bounce to its high, which would be VRail, positive VRail. And then it has a lower threshold that when your input hits that, reaches that point, it bounces downwards to its low point, which would be negative VRail. But we have a non-inverting, we have an inverting Schmidt trigger here, which causes, when you hit the lower threshold, it bounces to its high state of positive VRail, and when you hit its, did I say lower state? When it hits when it hits the lower threshold, it goes high. When it hits the high threshold, it goes low. And so here we have a graph that would show that. So here we have our input in yellow. When it goes down to a certain, when it goes down to the lower threshold here, we see that our output in blue goes high. Then when our input reaches this high threshold here, our output bounces down to its low state of negative VRail. So we see those values correspond to a V1 and V2 that we're interested in of 2.4 and 0.7 volts. respectively.
As our upper and lower threshold voltages.
Yes, as the threshold, for our inputs of V1 and V2. And that corresponds to a positive rail and negative rail. The positive rail would be around 4.36 volts, and the negative V rail would be around negative 3.05 volts.
And that's the output of the Schmidt trigger, the positive output, and the negative output is 4.36 volts and negative 3.05 volts, so that's what we see with our output of the Schmidt trigger. The Schmidt trigger is a particularly useful circuit because if you oscillate around one input, one threshold, you go above the upper threshold and you keep oscillating around that threshold, nothing happens because you need to go past the second threshold to get back down to the other voltage.
Yeah.
Meaning that if there's a little noise in the signal, in the input signal, it doesn't really matter. It doesn't affect the output as much because you need to oscillate between the two thresholds, go above the upper one and below the lower one to actually change inputs repeatedly.
It's sort of like a primitive error correction or error aversion method for your inputs.
This is the rest of our VCO. So we have the current source and the Schmidt trigger. The output of the Schmidt trigger goes to an inverter, which is this, which we use as another op amp over here, and we have these resistors here connecting it to VCC and everything to make this inverter work with this diode and everything. And then we have the current mirror here with these two diodes connected to the matched pair BJTs over here with the bases tied together as well as the emitters tied together, and that connects to the inverter as well to make our circuit work. And crucially, we have this capacitor here which connects the input of the Schmidt trigger to ground so that the constant current into the input of the Schmidt trigger can correspond to a linear increase and decrease in voltage, a constant increase and decrease in voltage, because the rate of change of voltage is equal to the current, and the current is constant because we have a constant current source dependent on Vn. So that corresponds to this graph that we have here. This graph. So this is the yellow line is our input to the Schmidt trigger, and the blue line is the output of the Schmidt trigger. So we see the voltage increases linearly with the constant current because of the constant current source, and then once we reach the upper threshold voltage, the output goes low to net V minus rail, and then because of the current mirror and the constant current source, the voltage into the Schmidt trigger decreases linearly as the capacitor is discharging, and then once you get to the lower threshold voltage because of the inverting Schmidt trigger, the output then goes high again to V plus rail, which was again around 4.3 volts and negative 3.3 volts for V minus rail. So here the capacitor is charging and here the capacitor is discharging. Constant linear increase in the input to the Schmidt trigger corresponds to these the square wave output of the Schmidt trigger, making our VCOs. And this was for 4.5 volts for V in, and it has a period of about 2.6, 2.7 milliseconds. But again, this period changes, the frequency, twice 2.7 milliseconds, I guess, because it's the full period, so I guess around 5.5 milliseconds or something. But again, this period and frequency change as we change V in, because that's what a voltage controlled oscillator is. Okay, thank you.